If you find yourself making custom circuit boards, you probably know this feeling. You've poured so much effort into the design, scouring data sheets and crafting the schematics. You paid attention to every detail during layout, tweaking parts and traces until they were perfect. You sent your design off, and then 2 weeks later, an envelope arrived, stuffed full of beautiful PCBs, with crisp silkscreen and perfectly plated pads. In your excitement, you work through the night, populating the boards, your workspace filled with the smell of flux. And suddenly, you're done. There's your design, the subject of so much passion and so much effort, sitting on your bench, completed. And then comes the scariest part. Powering up a board for the first time is a truly nerve-wracking experience. You can be as careful as possible, probing every line with a meter, double and triple checking the schematic, setting your power supply with a restrictive current limit. Or you can just go for it. Flip on the supply and hope for the best. Either way, those seconds after that switch closes draw into an eternity, until suddenly you're met with the success of LEDs flickering to life, or the disappointment as components give up their life force in the form of rancid smoke. Perhaps this doesn't have to be quite so exciting though. What if you could incrementally test your boards, check out the correctness before committing power to it? Careful probing and analysis is one option, and that's certainly viable for small numbers of boards. But if you're making production quantities of something, even just 100 for an ambitious hobby project, you need something a little more automated. And that is why I made this, the universal PCB program and test fixture. Forget your multimeter. Electrically connect this to the board, and this will check for short circuits and make sure the resistances are correct between pins. You can then use this to program your microcontrollers, boot them up, and do functional checkups, just to verify that everything operates as intended. Today, I'm going to cover the design and operation of this tester. Follow with me through this, because if you like what you see, I'll be releasing this as open source, and you can build one for yourself. Let's get into it. So how does this all work? At a high level, you write a script in a text file to tell the tester which tests to run. It runs the tests, notifies you of errors, and writes a log file that you can check to assess the functionality of the board under test. So far, I've only implemented a few commands, but you can do things like create a header with general information, check the resistance between any pair of pins, check all pairs of pins for shorts, and run custom functions, which you added the code yourself. I'm hoping to expand this set of commands, but I'll get to that later. Let me show you how quick and easy this is. Here's the input file I've made. This is just a normal text file, nothing special, with the vertical bar character being used to separate arguments. The first line is the header, which names the program, it gives a name for the output file, and it has a field for arbitrary text to print into the log file, as well as these two arguments. These are not implemented yet, but the idea is that one tells the software to log the time of day that it was run, and the other one implements a counter, which will count every time you run that script. So you can use it like a serial number. These last two fields are designed to allow runs of boards to be tested back to back, all in one output file, while still being able to track which data goes to which board. Next, there's a write command. This simply writes text to a line in the log file, and it's useful for making the output file a bit more readable. Then we get to the short command. This checks the resistance between every pair of pins to tell if they're shorted or not. This 10 argument is the threshold for what is considered shorted. Anything less than this, 10 ohms in this case, is considered a short. Finally, there is a comma-separated list of pins to skip. These pins aren't hooked up on my board, so why bother measuring them? Then I've got an impedance measurement command, which is really just measuring resistance. So this line measures the resistance from pin 0 to pin 1 and verifies that it is between 500 and 10,000 ohms, as set by these arguments. This last argument tells the script what to do in the event that it falls out of range. Log cont here means to log the error and continue the script. Finally, there are these custom functions. Now these are up to the user to implement in code, but the second argument specifies which custom function to use, as you can have up to 255 of them. There are also two general arguments that you can pass on to those functions. For my first project with this tester, for example, custom function 1 commands each LED and reads a photodiode to ensure that those LEDs light up. Custom function 2 turns on a speaker and checks the response of the microphones on the PCB under test to verify that they're working. I'm not using the optional arguments in either case, so they're just ignored. I'll place this file into an empty SD card, properly eject it since I'm on camera here and all, and then I'll put it in the tester. Power it up over USB, and the tester will present this GUI. I'll just click Run Program, and that's it, in real time. In this case, it made 56 resistance measurements, it checked out 6 LEDs, and it turned the speaker on to check out the microphones. All that in what, 3 seconds? Here's an example of the output file. These first 3 lines are the header info, then this text I added to demarcate sections. Next is the short circuit check. It logs the resistances of each pin combination. In the future, I plan to add an option where it will only log results if there is a short, but at the moment, it's logging everything. Then there's a resistance measurement between pin 0 and pin 1, which passed. And finally, the LED check and the microphone check, both of which were successful. As far as what's going on the board, don't worry, I'm not going to drag you through the schematic, but I do think a quick whiteboard description would be useful. At the center of all this is an off-the-shelf microcontroller board. I'm using an STM32F4 Nucleo. Most of what this is doing is running the display and the interface, but it's also switching multiplexers, talking to the ADC, reading and writing the SD card, and interfacing with the circuit board under test. Arguably, the most important thing this board does is measure the resistance between 2 pins. There are many ways to do this, but as far as I know, they are all based on Ohm's law. There are 2 obvious solutions to find R here. One is to set the voltage and measure the current, and the other is to inject a current and measure the voltage. Another method is to set up a voltage divider with one known resistance, and then measure the divided voltage and calculate the other resistor. Now, measuring voltage tends to be easier than measuring current. In fact, you typically measure current by measuring the voltage across a shunt resistor. So that knocks one approach out. The other 2 are both valid approaches, but for this project, I've chosen to inject current and measure the voltage. There are many ways to create a current source, but I suspect the easiest is to pay 34 cents for a purpose-built IC, so that's what I've done. I'm using the PSSI 2021 SAY, which, when operated at 5 volts, can output between 50 microamps and about 5 milliamps, depending on the value of the set resistor. To get better resolution, I want to change the current depending on the load. So rather than just having a single set resistor, I'm using a TMUX 1511 to switch different resistors in. Now, despite the MUX in the part number, this isn't actually a multiplexer. It's really 4 individually controlled MOSFET switches, which means I can switch on multiple resistors in parallel to get more than 4 resistance values. So I did what any engineer would do, and I created this illegible spreadsheet to optimize these values. So I've got the current, but I need to inject it into a pin, then measure the voltage difference relative to another pin. To do this, I'm using a series of multiplexers, actually multiplexers this time. I'm using 2 8-to-1 muxes per side so that I can select any of the 16 pins on the current injection side, and any of the remaining 15 pins as the ground reference. With 3 signals and 1 enable on each of the 4 multiplexers, I would quickly run out of I/O lines on the processor, so I added an I2C GPIO expander to handle setting these. To measure the voltage that results from injecting current, I added an external ADC. I'm using the TI ADS131M02, which is a 2-channel, 24-bit sigma delta ADC, and it also integrates a programmable gain amplifier into the front end. At less than $3 for quantity 1, this thing's a great deal, but it does have some oddities that I'll discuss later on, and one limitation that I missed when designing this project. Besides the resistance measurement circuit, this incorporates user buttons and a rotary encoder, as well as a 160 by 128 full-color OLED display. This display is a little small in hindsight. I should have used something bigger. I decided to use the Light and Versatile Graphics Library, LVGL, to program this, which I also have opinions about that I'll get to in a sec. The last thing this does is switch and buffer signals. I'm again using the TMUX 1511 for this, and a Unity Gain op-amp for buffering. By switching signals in and out, I can isolate the 16 pins while I'm measuring impedance, and then I can connect them to things like the debugger when it's time to program the boards. I've also added 3 BNC outputs to send signals out to external instruments for probing. 2 of these are discrete analog outputs, and the third can be connected to any of the 16 impedance measuring pins. Once I had the concept done, I made the schematics in KiCad, I laid the board out, and then I sent it off to the sponsor of this video, JLC PCB, to be manufactured. Ordering from JLC PCB couldn't be easier. Simply drop the zipped Gerber files into their quoting tool, and it will recognize the number of layers and give you an instant quote. Now, this is a 6-layer board, as the right side of this board is quite busy and there are a number of serial interfaces that really benefit from having solid ground planes. Luckily, JLC PCB provides affordable 6-layer boards that come standard with advanced features like VIA in-pad. There are tons of customization options as well, such as PCB thickness, solder mask color, temperature rating, copper weight, and on and on. You can get your circuit boards with the exact features you need, all at a great price that won't blow a hobbyist's budget. JLC PCB also offers great solder paste stencils, PCB assembly, even 3D printing and CNC services, making them a one-stop shop for your next project. Check them out through the links in the description, which come with a bunch of great coupons to help save you money on your next project. When the boards arrived, I started assembly, which was a nightmare of my own making. For my first mistake, I decided to make my own stencils using my fiber laser. Now, this is a fairly large board, so any small errors in the laser were really amplified at the edges, which necessitated a very careful calibration of my laser. Even after that, a number of the smaller features near the edges just didn't turn out well, like the tiny pads on the TMUX switches. After the stencil failed, I attempted to apply solder paste by hand to some of these, but that also turned out poorly. I ultimately had to rework these by hand using a hot plate and a hot air pencil, as I didn't use footprints that were hand solderable either. This was really frustrating and really hard to inspect. There are also a couple of LDOs on this board that have thermal pads under them. Those were a real nightmare. Even using a hot plate, I struggled to get enough heat into the board. I spent several very frustrating hours getting these parts soldered correctly. So what did I learn? Well, first, I've gotten better at soldering over the last couple of years, to the point where I felt like I could handle even the smallest SMD components. I actually went out of my way to get small packages for this board, even though there was plenty of space for some odd reason. Not only did this make it harder to solder, but also harder to lay out, and the parts were more expensive. I've learned my lesson though, so in the future, I'm only going to get the tiny packages if that's all that's available, or I actually need to save the space. Otherwise, I'll stick with things like SOIC packages, which are just a breeze to solder. And if I do end up with QFN parts, I'm going to modify the footprints so I can rework them with a soldering iron if I need to. Once I had it soldered, I modeled up and 3D printed a case, pressed in some inserts, and got it assembled. Now that this is together, let me show you how this interfaces with your PCB under test. If you watched my last video on pogo pins, you probably saw this little adapter PCB I made to connect to some flexible boards. Now, these are from my tile backsplash project, which I'm going to be getting back to soon, so please subscribe and be sure to go watch those if you haven't. Anyway, this pogo pin board is designed to connect with this fixture, but you're not limited to pogo pins. The interface on this is a 2x8 header for impedance measurement and a 2x10 header for power, ground, GPIO, and then dedicated analog pins. So anything that can connect to these headers can be measured. Any other adapter PCB could be used, whether it has pogo pins, headers, edge connectors, whatever really. You could put this header arrangement on your final PCB and then forego an adapter PCB altogether. You could even connect cables to these and route them to your target PCB that way. The beauty of this approach is that it's versatile and it can be adapted to nearly any project. Let me draw the pins out. The 2x8 header for impedance measurement is very straightforward. You hook these up to nets on the PCB you're testing, and it allows you to measure the resistance between any two of the 16 in either direction. A few of these are special though, as they can also be hooked up to the debug probe. These 5 pins are explicitly designed to be VDD, ground, reset, serial wire clock, and serial wire data. And these signals can be switched to the outputs of the ST-Link that is built into the new Clio. This means you can use this fixture to program your boards as well, albeit with the help of a computer and the appropriate IDE. If you're not programming an ARM microcontroller that uses the SWD interface, then you should also be able to route these pins to an external debugging probe. The 2x10 header is designed to connect to additional circuitry on the adapter board, which is up to you to add for your exact application. This interface contains the usual 3.3 volt and 5 volt rails, as well as ground. It also has 4 analog lines, and you can route them to these 2 BNC connectors that I mentioned earlier. You can hook these up to nets on the target PCB or to circuits on the adapter PCB. I'm doing both of those on the Tialite board. 2 connect to analog microphones on the circuit under test, and the other 2 go to photodiodes on the adapter PCB. There are also 4 GPIO on the connector. These can be used for whatever really. For instance, I'm using 2 to drive a speaker on this design. 2 of the pins have timer and PWM capability as well. Finally, there is one SPI interface and one I2C interface. These unlock tons of potential, from GPIO expanders to ADCs or DACs, microphones, speakers, memory, anything that can communicate over these interfaces. It's worth noting that these GPIO and interfaces are up to the user to implement in code, with the exception of forwarding the analog signals to the BNC connectors. Speaking of code, there's a lot of software on this thing. Tens of thousands of lines of code, which I've been working on for over a month. I definitely underestimated the level of effort this would take. I'm not going to drag you through all this, I'll just hit the high points. First, I wrote all of the drivers for this, of course with the exception of LVGL and things like the file system. I wrote code for the ADC, the GPIO expander, and the display. And these were mostly straightforward, although I found the ADC to be interesting in that it responds to any command with the ADC readings, but on the next cycle. So if you write a register, for instance, it responds with some data that verifies the write, and then it gives you the ADC readings. If you read a register to get its value, it sends you that value, then it sends you the ADC readings. To get just the ADC readings, you actually send a null command, and then you get the ADC readings on the next cycle. Now don't get me wrong, this works totally fine. It was just a little confusing to me at first. I also had endianness issues with the OLED display, and I had to correct those in software, which is horribly inefficient, but I'm running the processor at 180 megahertz, so I can get away with it. I had a few issues with the graphics library, LVGL. First off, I'm using LVGL all in code. GUI-based design tools exist that write LVGL code for you, such as SquareLine Studio, but I'm not using those. Second, this is the first time I've used this, so don't count me as an expert. That said, I found the documentation to be fairly good. There were decent examples, but this is a really complex library, and there are tons of cases that just aren't covered in the documentation. There is a forum, but my questions were often there but not answered, and that seems to be common. The biggest issue I had was that I'm using a rotary encoder to navigate through the screens, not a touchscreen, and this only seems to be supported by a subset of the available widgets. It's not really clear which ones support rotary encoders and which ones don't, so I wasted a lot of time trying to get certain widgets to work. Also, don't underestimate the amount of time adding a GUI takes, even if it is built by a library. That said, I think this GUI looks great for the amount of time I have in it, and I intend to use LVGL in future projects. I mean, just imagine trying to code all this from scratch. There was also the general slog of software and debugging. I wasted entire nights debugging, from the compiler randomly optimizing and removing things I needed, to having too few DMA channels, to needing more than every pin on the Nucleo and having to get a little creative. There's probably a bunch more things, I just blocked them out of my memory. As far as hardware troubleshooting, it was actually pretty straightforward, but there were still a couple issues. I first tested the resistance measuring circuit using this resistor decade board, which there's a link for in the description, as well as links to other things I use and recommend. I was getting crazy errors, on the order of 50% or even bigger. I tried a ton of things, tweaking software and probing components. Finally, I removed a protection diode on the input to the ADC, and everything worked right. I made a classic mistake here. I assumed that the diode was ideal, only transmitting in one direction with a small voltage drop, and not allowing any current in the reverse direction. This is of course not true, particularly for the Schottky diode I was using, which had around 100 microamps of leakage current where I had it biased. With the current source only delivering 50 microamps at its slowest setting, adding a stray 100 microamps caused huge errors. The fix was pretty simple, I just left the diode off. I didn't have any issues with the ADC unless you count my inability to read the datasheet. I assumed this ADC would read from 0 to VDD, but it actually reads plus minus 1.2 volts. This limits the highest resistance I can measure, and currently I can only measure 80 kiloohms. I plan to fix this range issue on the next iteration of the circuit board. Amazingly, there are no white wires on the test fixture board, which is surprising because I was in a bit of a rush to get this out the door. I did need one white wire, or rather solder blob, on the adapter board though. This signal is what commands the speaker, and the original pin was not connected to a timer with pulse width modulation capabilities. Luckily, the pin next to it was, and it was also unused. So I blobbed them together and I set the original pin to be high Z. Another thing that caught me multiple times were the jumpers on the STM32 Nucleo. ST designs these to be pretty universally adaptable, but they configure them by default in somewhat questionable ways using 0 ohm resistors. You have to very carefully study the documentation to set these appropriately, as I found out the hard way. First, they connect to the external oscillator by default. I needed those pins as GPIO though, so I had to switch a couple jumpers around. One that really took me some time to figure out was that PA2 and PA3 are hooked up to the serial port on the ST link by default and not to the headers. I plan to make some in-depth documentation on this project where I will be sure to outline the state of all these jumpers. At the beginning, I showed the execution of a test program, which is probably the most useful thing this device does, but let me walk you through some of the other features quickly. Using the interface, you can manually run many of the commands, such as measuring the resistance between two pins. You can also swap the analog output between the A channels and the B channels. Let me demonstrate why this is useful. In this design, I have the B channels hooked up to these photodiodes that verify the LEDs work. If I switched the analog outputs to the B channel, I can then hook an oscilloscope right up to this BNC, just making sure my scope is in 1x mode here. Now I can very easily monitor the photodiodes. If I shine a light on the diode, we can see the signal moving, indicating this is working correctly. The debug probe option connects the power and SWD interface from the ST link to the target PCB, or you can use an external debug probe if you desire. This allows you to program the board and then use the power and run it. Right now, this is not latching, so to speak. As soon as I leave this page, it will disconnect the debugger. I need to implement some additional logic, perhaps even a dedicated button for this, as right now you can't leave the debugger connected and then go do something else in the menus. Unless you manually code it, that is. Regardless, using the onboard ST link is working great for me. I'm actually programming a Puya PY32 here, so I figured the ST link wouldn't work as they're typically restricted to STM parts. This wasn't the case though. I connected it up, selected debug probe in the menu, then jumped over to Microvision and hit load. And just like that, it worked. There's also the option to send any of the 16 resistance measuring pins to the third BNC connector. At the moment, I can't show this off, because there is no power to the board without the debug probe connected, and as I mentioned, I can't leave that connected. This is one of the next things I'm going to be addressing in software. As this stands, it's working quite well, but it's not perfect. I often feel that when you watch a video of somebody showing off a project, it probably works less well than they're letting on, because making anything truly reliable is a tremendous undertaking. When you're shooting a YouTube video, though, you can always do another take and hope it works correctly that time. In some regards, that's the current case with this, as there are a few sporadic issues. For instance, there's lots of error checking going on in the code, but there's not a lot of error handling or reporting. Errors either exit the function without notifying the user, or they end up in an infinite loop. I just haven't had the chance to go find all these error cases and write the appropriate handlers, but it's on the to-do list. Right now there are only 5 commands, but I've got ideas for several more. Some of them are relatively simple, like a command to set or reset one of the GPIO pins, or to use the STM32's ADCs to read one of the analog values and write it to the log file. There could even be some more complex commands, like using the timers to create a function generator on one of the GPIO pins. There's no reason there couldn't be a command for a 1000 Hz square wave, for instance. Other than that, I just haven't written the code yet. Something like a diode check would also be really easy to do. Another thing I need to do is respin this circuit board to fix a couple of limitations. One, I'm going to go from a 4-wire SD card interface to a single-wire one. This will free up some pins, allowing me to use the external oscillator maybe, or perhaps add some LEDs or more buttons. I also need to add a bunch of test points. In my haste, I neglected to do that. I'm also going to figure out a way to measure higher resistances, ideally up to like 10 mega ohms, as 80 kilo ohms is just way too low. I wouldn't mind going to a larger display either, as this tiny one seems straight out of the early aughts. Finally, I'm going to switch out the tiny QFN parts with easier to solder equivalents. Lastly, I'd love for this to be a totally self-contained programmer, where you could save a hex file onto the SD card and then program that onto the target device, all within this. This seems like quite an undertaking though. I'd have to hack through the debug probe code and get an in-depth understanding of how the SWD interface works. But still, this is a dream of mine, and if you've got any insight, let me know in the comments. I'll be releasing this hardware and software as open source in the near future. So if you're interested, be sure to subscribe, as I'll be posting an update video when I do that. I'm curious if anyone else thinks this is useful, and if they'd be interested in buying a kit or a partially assembled board. I'm not really in that business, but I could be convinced if there were enough interest. It has taken a lot of effort to get here, but I'm really happy with how this has turned out. This is going to save me a ton of time programming and debugging boards for my upcoming projects, particularly the tile backsplash, where I need to make a few hundred boards. I'm not going to say there aren't issues with this, but it's doing everything I'd hoped, actually more than I initially envisioned. I'm going to continue to polish this up, and I'll provide an update and publish the design in a future video. That's all I've got today. Be sure to like and subscribe so you can stay up to date. Thanks for watching.